I didn't assign these ones. I thought I'd save it for today's class. And okay, what am I trying to do here? Okay, I'm multitasking. I'm really bad at multitasking. If I try to do more than one thing at once, then I do 0 things at once. Okay, let's see. Okay, AP Calc. Okay, embed. Aha. Here we go. And publish. Okay, there we go. Okay, let's get started. Hope you guys. Oh yeah, go ahead. What's up? Oh yeah. I'm just I was multitasking. I'm gonna try to make these all like the same size and excuse me, a little more readable. Yeah, you're welcome. So these are questions from Unit 6. These are free response questions. So like I don't know if you were around, but I was just telling one student that these are part B of Unit 6. So the way the I guess the progress checks work. Now my pencil doesn't want to work. Come on. What the heck? That's not good. I need my pencil to work. Yeah, maybe. Uh-oh. What's going on here? Okay, let me turn Bluetooth off and then on again. That's not good. Oh, here it is. Now it's working. Okay. So yeah, the way the free response questions go is you have a unit, right? So this would be Unit 6, and then they have multiple choice questions, and then they have free response questions, as you know, and then there's usually part A and part B for each of these, and sometimes there's even a part C. So this one is part B of Unit 6. So we're going to do Unit 6 free response part B together. And I thought we could do the first couple together. And then after that, I think I would like you as the exit slip to do part D on your own, and I'll give you a little hint as to where to get started with part D. But yeah, as you may know, Unit 6 is just a whole whack of integration. So there's a whole lot of different integration techniques, including, as you can probably tell from this first question, Riemann sums. So that's what we're going to start off with. Let's just what I thought maybe we could start off with is where is it here? Just a list of all the topics from Unit 6. So we'll kind of carry on with our little study guide. So let me just pull that up. AP package, units. So yeah, Unit 6, and I'll just kind of write this. Maybe what I'll do is I'll insert a page underneath here. There we go. Okay, so let's write out what the topics of Unit 6 are. So Unit 6 is integration and accumulation of change. So Unit 6 is integration and accumulation of change. Right, and that's really what integration is, right? Is that you're looking at how change is accumulated, right? Like a function could tell you how much money you make every day, right? That could be your function. But then as that money accumulates and you collect it and you add however much money you make every day, that would be like the integral, right? So you're kind of accumulating all of these values over time. So it looks like there are 14, ooh, lucky you, 14 subtopics in Chapter 6, or Unit 6. So let's just quickly list them. So the first one is exploring accumulation of change. So let's just write accumulation of change. Okay. 6.2 is Riemann sums. Riemann sums. Okay. So approximating areas with Riemann sums. 6.3 is more Riemann sums, but then with Riemann sums there's also, I'll just write RS, there's also summation notation. Okay, and we've got a lot of experience with sums. And then integral notation. Okay, so like, what do those integral symbols mean? All of that fun stuff. Number 4 is the fundamental theorem of calculus. I'm going to write FTC. Fundamental theorem of calculus. Kind of sounds like an important theorem. Interpreting the behavior of accumulation functions involving area. So, how do you summarize that? Let's just look, say, interpreting behavior. Of accumulation. I'm going to write accumulation functions. Okay, so effectively, like how do integrals like how do integrals react with respect to the properties that a function have? Okay. Okay, so that's 6.5. 6.6 is definite integrals. And the properties of those. Properties. Okay, 6.7. 6.7 is more fundamental theorem of calculus, but it's with respect to the definite integral. Okay. 6.8. 6.8 is finding antiderivatives and indefinite integrals. So I'll write derivatives, and indefinite integrals. Indefinite integrals. Okay, 6.9. 6.9 is, let's see, okay, I'm going to have to insert one more page. There we go. Yeah, what's up? With respect to. Number 9 is integration using substitution. So I'm just going to write substitution, because we all know what substitution means. Okay, and number 10, integrating functions using long division and completing the square. I'm just going to write long division, completing the square. And we've done a few things like this. I think this is a topic that we did together. Now, I don't remember, did you guys prefer long division or did you use synthetic division? Synthetic? Okay, so sounds like most of you like to use synthetic division. Great. Okay, so yeah, so synthetic division is great. I tend to prefer long division, but that's just my own preference. The reason I prefer long division is because there's no question about how it works. I have difficulty understanding how synthetic division works when your divisor is non-linear. Like I can use synthetic division, pardon me? Then you use long division. Yeah, exactly. So I prefer just to have one algorithm. I think that there is ways of using synthetic division with a non-linear divisor, but I always forget how to use it. It seems more complicated than it needs to be, because the whole point of synthetic division is to make it simple, right? But then if it all of a sudden isn't simple anymore, then what's the point? So that's why I prefer long division. But if you have a lot of experience with synthetic division and you're good at that and that's what you prefer, use that. Absolutely use that. Number 11 is, and this is a BC only topic, but we are all doing BC. So this is integrating using integration by parts. Awesome. So integration by parts. Everyone's favorite way of integrating. And then 6.12 is integrating using linear partial fractions. Awesome. Partial fractions. Okay, so that's kind of like where you do the opposite of factoring a fraction, or the opposite of simplifying a fraction. Kind of split it up. Number 13, and that's something that we did, I think, like maybe 4 weeks ago. Evaluating improper integrals. So improper integrals. And that's just where you're sort of forced to use a limit. So it's kind of like where the fundamental theorem of calculus doesn't really apply because you have a point of discontinuity, or if your endpoints are positive or negative infinity. And then 6.14 is, well, just the general techniques for integration. Okay, so I mean, in pretty much any calculus textbook, you'll always find sort of like a wrapping it up all together sort of section where it's like, okay, so you learn for the past couple of months, you've learned topic after topic on like, oh, this is how you would integrate this weird function. Oh, what you have the fundamental theorem of calculus doesn't apply. Well, you use this. Oh, you've got this weird sort of rational expression. Well, used by parts. Use partial fractions, and then you've got all these different situations, and then the last bit is just putting it all together. So like integrate this integrate this arbitrary function, and you're not told what you're supposed to do, right? It's not like, oh yeah, use partial fractions to solve this. It's just solve this integral. So that's it. So those are the 14 topics of Unit 6. So I think that the question that I've selected here, well, it uses Riemann sums. So we're going to take a look at, I guess, 2. And I suppose it kind of bleeds into 3 as well. So for part B, we will use the fundamental theorem of calculus. So that would be this one here and this one here. I suppose it kind of bleeds into here as well, and definite integrals and its properties. For part C, okay, there's an indefinite integral. So you can see how many, and I guess the whole accumulation of change, that's all of this. Antiderivatives and indefinite integrals would be that one. And for this part D, well, I don't want to give it all away, but here we go. And then since we're not told what to do, even though I just told you what to do, that would be techniques. So this one question covers pretty much the whole unit, different sort of little areas of it. It's not a super deep investigation of each one of these units. It kind of just scratches the surface, but it does cover a lot of the units. There's no long division or completing the square. There's no integration by parts. Oh wait, actually, I shouldn't have told you this. I think it actually is integration by parts and not substitution. So, but then again, I just told you how to solve it. Anyway, so this one question covers a lot of Unit 6. So I think it's a good question. So let's jump into it. Let's kind of quit the banter and let's get going. So let's start off with question A. So question A. So let's remember what our function is. So I know that f of x f of x is, well, let's just read the question actually. You guys probably haven't had the same amount of time to read this as I did. So we're given this function. This function is 4 over x squared. And we're asked to integrate this function from 1 to 12 using a left Riemann sum with these subintervals of 1 to 4, 4 to 8, and 8 to 12. Okay, so we have 3 subintervals, and in this case I think it's interesting because they're telling us exactly what the intervals are. And you'll notice that the length of each one of these intervals is a little bit different, right? Like the distance from 1 to 4 is 3, the difference from 4 to 8 is 4, and the difference from 8 to 12 is 4. So they're not perfectly split up, right? So I think that's kind of interesting. So this is the Unit 6 free response question part B. So I assigned part A already. By the way, I think over the weekend a lot of students seemed to want me to open up the remaining units. So I know that we decided last week we weren't going to do that, but there was only one more unit that hadn't already been opened because I'd opened up like unit, what was it, 7, 8, and 10. I'd already opened those up while we were still studying those. So we only had the unit 6 to open up. So I opened up unit 6. So now, if you want, you can complete the rest of the free response questions. I would recommend doing 1 per day. That would be my recommendation, but you're free to do whatever you want. Yes, because 9 is on polar coordinates, so we're going to skip 9. 6, 7, 8, and 10. That's correct. Yeah. Okay, let's try this one. So f of x is this function. What is it? 4 over x squared. We've got 4 over x squared. Okay, and okay, so let's think about what this function is going to look like. I believe it looks something like this, and I'm just kind of eyeballing it. So it looks something like this, right? We have some kind of vertical asymptote. Yeah, so you got a stretch factor. So this would be like the point, like when x is equal to 1, then y would be equal to 4. So this is the point 1, 4, etc. Okay, so yeah, that's the general shape of our function. I guess you could say that we have a horizontal asymptote at 0 as well, if you really wanted to go there. That's not really what we're asked to do, though. We are asked to approximate the integral using Riemann sums. In fact, left Riemann sums with these subintervals. So we are going to use the subintervals, what were they? 1 to 4, 4 to 8, and 8 to 12. So let me think of which color to use. How about orange? So we're going to go from 1 to 4. So I'm like, there's no scale to this drawing. I'm just kind of eyeballing it here. And let me kind of extend my graph a little bit. There we go. Okay, so we're going from 1 to 4. We're going from 4 till 8. So 4 till 8, it's like right there. And then 8 to 12. So let's say that that's there. Okay, so here's 1, 4, 8, and 12. And we are using the left Riemann sum. So that means that we take the left-hand endpoint. So that would be, in this case, this box right here. In this case, this box right here. Right? And then over here, it would be this box. Okay? And this is just a very rough sketch. But I just want to draw a little diagram to give you some idea of what we're asked to do. So the thing that we're asked to approximate is the actual integral from 1 to 12. And that actual integral is this sort of shaded area here, right? It's the area underneath this curve. But we aren't going to calculate it exactly. We're going to instead approximate it by calculating the area of these boxes. Oh, sorry, just my neighbor must be doing something upstairs. Okay, so we're going to calculate the area of each one of these boxes. You can tell just by looking at the diagram that we are going to be overestimating, right? So our approximation is going to be greater than the actual integral, right? Because each one of these boxes is bigger than the area that it's supposed to be approximating. So you can see all of this sort of blank space here. So this is like what I'm drawing here in green. I don't know if it's showing up in the video very well, but that's the amount that we would be overestimating. So in each one of these boxes, we're overestimating. So I mean, there's several ways we could do this. You know, if you want, you could make a table, right? You could have some kind of table going like this from here to here, right? You could have x, you could have f of x, and you could have the area, right? The area from one endpoint to another. What I want to do, I don't want to do that. What I want to do, I just want to make sure that we completely understand what we're doing here. So what I want to do is I just want to calculate the area of this, the area of that, and the area of that. And the reason I want to do this is because I think it's important when you're doing these questions, especially in the context of like an AP exam, to show all of your work and to show all of your understanding. So if we're able to sort of draw a diagram and look at the area of each one of these sections and demonstrate that we understand what that area represents, then I think that that's the best way to make sure we achieve all of our marks. So this area here, I'm going to call this area 1, or A1. Well, that's going to be, well, the distance from 4 to 1, so 4 minus 1, times the function evaluated at 1, so I'll write f of 1. Okay, that's what the first area is going to be. So maybe I'll write A1 here, and A2 here, and A3. So the first area, that's going to be 3 times, well, f of 1 is going to be 4 over 1. So 4 over 1, which is 12. Okay, so this first area has an area of 12. Okay, maybe I'll kind of move this over here. Okay, and area 2 is equal to, well, the length of this little rectangle is 8 minus 4. 8 minus 4, right? That's what this area here represents, right? That's the distance from here to here is 8 minus 4, and the height of it is the function f evaluated at x equals 4. So that would be times f of 4. And, well, 8 minus 4 is 4, and f of 4 would be, well, we would have 4 over 4 squared, which is 4 over 16, which is 1 over 4. So this would be 4 times 1 over 4, which is equal to 1, which is nice. For these types of questions, if you're getting integer values as your solution, that's a good sign. It's not like you can be absolutely sure that your answer is correct, but it's a nice, validation that, okay, I'm getting integer values. This is working out nicely. So the next one, the third area would be, well, I would do 12 minus 8. I think my head is probably in the way there. There we go. Okay, so 12 minus 8 times, well, we are going to be evaluating the function at 8, where x is equal to 8. So that would be f of 8. F of 8. And that is equal to, well, 12 minus 8 is 4. And f of 8, let's quickly calculate that, would be 4 over 8 squared, or 4 over 64. And 4 goes into 64 16 times, so this is 1 over 16. This is 4 times a 16th, which is 1/4. Okay, so I've calculated the area of these 3 rectangles. So the total area, is, what was it, 12 plus 1 plus 1/4. 12 plus 1 plus 1/4. So you could either, you could write 13 1/4, or you could convert to a decimal. So what would that, or not a decimal, yeah, you could do a decimal actually. You could do 3.25, or you could do, what am I trying to say, improper fraction, which is what I would prefer. So that would be 48, 52, 53. 53 over 4. Yeah, so that's that question. Any thoughts or grievances about this one? Mm-hmm. Yeah, there you go. I'll leave them up for a few seconds. Yeah, these are the questions there. Yeah, so we just did the first one. I'd like to do the next two together, and then the last one, part D, I want you to do on your own. So let's calculate the actual integral. So part B is to say, forget about the Riemann sums. Let's calculate the actual integral. So we are going to calculate. So part B, we're going to go from, there we go, 1 to 12. What was it? 4 over x squared dx. Okay. So this one's not too bad. The first thing that I would like to do is just factor out the 4. So I've got 4 times the integral of x to the power of -2 dx. And so the way this one works is the exponent goes up, and then you divide by the reciprocal of that new exponent. So that would be, when the exponent goes up, I've got x to the power, so this is equal to, and we're going from 1 to 12, by the way. So I got 4 times x to the power of -1 all over 1 over -1, so this would be -1 times that. Let me just make this a little bit nicer. X to the -1. And we're going to take this from 1 to 12. So let's write this all out. So this is 4 times, well, I've got negative x to the -1. I'm just kind of writing it nicely again. 12 to 1. There we go. And let's split this up. So this is equal to 4 times, well, negative 1 over 12 minus negative 1 over 1. Okay, so in other words, plus 1. Okay, so this is going to be, well, 4 times, okay, so if I've got negative 1/12 plus 1, that's the same thing as negative 1 plus 12. So that would be 11 over 12? I think that would be 11 over 12. And that it would give us 44 over 12. And how close is that to our approximation? That'd be a nice little sanity check. Okay, let's see here. Yeah. True. That's 11 over 3. Thank you. And 11 divided by 3, it's about 3.6. What did we say it was? 13.25. Now I'm not so happy. It could be just that this was a gross overestimation, right? Because there's a lot of area here, but that still seems quite high. Okay, did I really make a mistake here? Yeah, the same thing. Okay, I can always verify my answers. I think I've got the College Board thing up. Yeah, let me quickly verify my answer here. But I'll try to do that in the background. I'll do some what do you call it? Multitasking. And you know how good I am at that. So, okay, we got one more, and then you guys are on your own for part D. So, we're going to find the value of this improper integral, right? So this endpoint goes way off to infinity. So we're going to have to attack it with a limit. And how about I get you to get a head start on part C, and then I'll catch up. Okay, so get a head start on this. Maybe start off by writing it as a limit and see where that takes you. So I am going to just verify my answer here. C. Yeah, I want you to get a head start on C. Yeah, looks like we got the same thing as the College Board, so and what I'd like to do as well, once we're finished this, I want to show you some of the things that they are expecting us to have written down. Okay. So I'm assuming you've got a bit of a head start already. Okay, so, oh, and now I can just look at the question up here. So just to reiterate the question, so here, this is me catching up now. So we're asked to integrate going from 1 to infinity of, well, it says f of x, but we're going to go from, I'm just going to write the whole function, 4 over x squared dx. And we want to either evaluate this or explain why it doesn't exist. And if it doesn't exist, it would be because the integral doesn't exist. Ooh, I've already got green. Ooh, come on. There we go. Okay, so let's start off by writing this as a limit. So I'm going to use the variable b because it's like the right-hand endpoint, and usually we go from a to b. So I'm going to say that this is the limit as b goes to infinity of the integral that goes from 1 to b of 4 over x squared dx. Now you could use pretty much any integral that you, or any variable that you want here because you're introducing it, but do not use x, right? It would be very confusing if you were to use x because x is already in your integrand, right? Because then you would be taking the limit as this goes to infinity, and then that it would be the same variable. So just choose any other variable. I would stick to the letter b. Kind of makes things easy to remember what's what. So let's integrate this, and we already found the antiderivative of this, right? So I'm just going to copy that down. So I've got the limit as b goes to infinity of 4 times, what was it? Negative x to the negative 1, and we're going from 1 to b. Okay, so let's evaluate this. I've got the limit as b goes to infinity of 4 times, well, this is where we would have negative b to the negative 1, or maybe I'll just write negative 1 over b minus, or I guess in this case plus, 1 over 1, so just minus or plus 1. Okay, so the limit as b goes to infinity, well, this thing would go to 0, right? So this is going to be, well, 4 times 1, which is equal to 4. So that wasn't too bad. Any questions about that one? No, it doesn't sound like it. Okay, cool. So I'm going to leave you with part D. But before I do, like I said, I want to just share a couple points with you. So I'm just going to pull up my iPad camera, and I want to show you. Here we go. Okay. I know it's kind of silly to be streaming from my computer using my iPad, and then it's like kind of like a full circle thing, but this is the best way I can think of doing it without too much extra headroom. So this is what they want you to write. So this is how it's marked. You have the choice from 0, so you can either have, where's my mouse? Here we go. So you can either have 0 points, 1 point, or 2 points. 0 points means that the student did not write a limit expression. So that would be saying, okay, and like recognizing that this is in fact a limit and writing this. So this is where you would get 1 mark, right? If you were to write the limit expression. And then the rest is just the answer, right? So if you're able to somehow, I don't know how you would, but if you were to manage to do this without taking a limit, then you'd still only get 1 mark. I don't think it's possible to do this question without a limit, but if you kind of manage to fandangle it without actually writing that limit, even if you got the right answer, you would only get 1 point. So that's how this one is marked. Part B, this one was just about the answer. Okay, so this one was just, and that's really all there is to this one, right? It's just evaluating an integral. That's all there is to it. This one here, though, so you get 1 point for writing the left Riemann sum, right? So that would be this material right here, and then the approximation is this. And I think when I mark these, I can check these off, like so. And I just want to share something with you for part D. And I'm going to scroll up because I don't want you to see the answer. But these are the things that they would be looking for in part D. Is your choices for U and dV, rewriting as uv minus v du, taking the antiderivative, and then the answer. So skipping steps here, I guess like what I'm trying to say here is skipping steps does not work for these exams. You're absolutely graded on your work. So show all of your work. Don't skip over writing your work. That is really important to show all of your work. So I guess that's what I wanted to just leave you with. So your exit slip for today is to solve this question here, and I'll leave it up so you can write it down. So it's basically the same integral. It's the same integral, except there's this extra ln of x, and you might think, oh man, that's awful. Ln of x, like throwing that in there, that makes it just not that nice. But think about how ln of x interacts with 1 over x, right? Like, what's the relationship there? Could you use that to, do integration by parts? Yes, you're going to use integration by parts, but how is that going to play into it? Don't forget to show all of your work, right? To demonstrate your understanding of how integration by parts works. Because even if you got the question wrong, you can still get partial marks for starting out by saying, okay, this is integration by parts, and this is how I have to do it. So, you get points for choosing a good u and dv for integration by parts. So, yeah, I guess we're gonna leave it at that. If you have any questions about it, let me know. So far, I haven't had too many concerns about the first 5 units. I think that one of them, the related rates question, there was a couple students who needed some help, and I was very, very happy to help. But since the weekend, I don't think I've had any other requests for like extensions or anything, so I think I'm just going to start marking them, and you should be able to see your results as they come. So I think what I'd like to do now is just sign out. And if you have any questions, then shoot me a message, and I'll talk to you guys tomorrow, I guess. Okie dokes. Any questions before I go? No? Okay. Bye-bye, guys. And bye-bye, YouTube. End.